Hey physics, welcome to another flipped lecture. We are here now in the classroom that we actually meet in, so you are able to tell that this is now the new academic year, but that's okay. We're glad to have you here with us as we're launching into chapter 15, talking about thermal energy and matter and how things interact when they get hotter or colder, how heat moves around. This is largely review. There are going to be some new math equations for you near the end that you haven't seen yet, but mostly in physical science and in chemistry, you have had almost all of these concepts before. So I am calling this a review with just a little bit of new information at the end. So let's dive into it. Okay, so the caloric theory was the first theory of heat. When people were wondering what is heat, the first idea was that it was actually a fluid, that it was an invisible fluid that flowed from one object to the other, and that fluid's name was caloric, or it was described as caloric. Caloric sounds like an adjective to me, but anyway, it was a invisible liquid, the caloric liquid. And that idea actually persisted a long time. It was only disproved, within the last 600 years. And so we've had this idea that it was a invisible fluid that flowed from one thing to the other when they came in contact with each other. And that model actually does explain a lot of what thermal energy does. The problem is that you can't see it, you can't detect its motion except that something gets hot. And so people started to scratch their head about it, like I said, about 600 years ago. And then more recently, some serious science was done on the question, and we now know that there is, in fact, no invisible fluid, even though that does, in fact, explain data fairly well. The new idea is the kinetic theory, and I don't know why on my slide it's a capital I, but it's the kinetic theory. And the kinetic theory is that heat is a movement of a form of energy. And just like sound energy or electrical energy, heat is a form of energy that can move from one object to the other and can change form and do work like other forms of energy can. So that kinetic energy theory as a model for explaining heat and thermal energy is the new way of looking at heat and thermal energy. So it is the accepted model today. It's based on a concept called Brownian motion, that substances are always in motion. Nothing is really sitting still. Even objects that look like they're sitting still are moving on the molecular level. And that random molecular motion is in proportion to the temperature. The hotter something is, the faster it is moving. And even solids that are sitting still in regard to how you and I can perceive the motion, the atoms and the molecules there are sitting there and vibrating or twitching at the molecular level in response to the thermal energy that they possess. The hotter they are, the more thermal energy that's present, the more kinetic energy is present at the molecular model, and the more that they are moving. Diffusion is a consequence of that. I'll show you a picture in a minute. When things spread out, naturally diffuse across a medium, that's because of the Brownian motion of the medium driving that object around. And I'll show you a picture of that in a moment. This was all proved by a very famous physicist, James Joule, and Joule did his work in many different fields. He actually was quite an accomplished scientist in lots of different disciplines. But with what we're looking at right now, he showed the relationship between kinetic energy and mechanical energy and thermal energy, and he showed that they were all linked. And he came up with a value for a calorie, which is the amount of energy required to raise 1 gram of water 1 degree centigrade. And he found out that mechanically you could produce that change in temperature by putting 4.186 Newton meters of energy into that gram of water. And the apparatus that he used is pictured in your book. It's kind of an interesting thing to look at and make sure that you understand. Later on, that unit, the Newton meter, was renamed in his honor, and we now call that a joule. So 4.186 joules of energy will raise the temperature of 1 gram of water 1 degree centigrade. So this is a picture of Brownian motion and the resulting diffusion of a particle. If the big yellow ball is some kind of substance and we are watching it diffuse, we're watching it spread out over time, The reason it's spreading out is because it is getting bombarded in all different directions by the medium that it's in. This could be something dissolved in the air or something dissolved in a liquid. And as the medium is experiencing Brownian motion, and here rather rapid Brownian motion because this thing is hot, the big, larger particle is getting pushed around by all of these bombardments, and it spreads out. It starts in the middle, but it doesn't end in the middle because it's getting pushed around by its medium. So diffusion that you have studied in chemistry and in physical science now makes sense in the light of Brownian motion and physics. Okay, so we now get into the concept of specific heat and specific heat and heat capacity. There you go. And these are ideas that have to do with how much energy do you have to put into something in order to get it to change its temperature. And that seems initially like a strange question, like any amount of heat should make something change its temperature. But that isn't quite the case. Some substances absorb a good amount of thermal energy before their temperature changes, and other substances change their temperature very readily with just a small amount of introduction of thermal energy. So how much thermal energy you have to put into a thing to get it to raise its temperature by 1 degree centigrade is a term that we call the heat capacity. And you can understand the word capacity there, meaning how much heat do you have to put into this object. And every object's heat capacity is different. It has to do with what the thing is made out of. It has to do with how big the thing is. It has to do with its shape, all kinds of different things. And so the capacity of an object to absorb a certain amount of heat energy before its temperature changes is the heat capacity. Now, some of the terms that we use there mathematically, we use a capital Q for the amount of thermal energy in joules that we're talking about. So whenever you see a capital Q in the next couple of chapters, you're going to be looking at the amount of thermal energy that we're dealing with, and that unit will be measured in joules. Okay, we use a capital C to talk about the heat capacity of an object. And the capital C, again, always different for any given object. It is talking about how much that object will absorb in joules before it changes its temperature. And obviously delta T is the change in temperature. So the equation that we have here, C equals Q of an object divided by delta T, means the more thermal energy I add in terms of delta Q for a particular object's value of C, the more the temperature will rise. And the larger the value of C for an object, the more Q I have to stick in before the T gets bigger, if that makes sense. Pause the video if you need to see that again and stare at that equation for a little bit. The heat capacity of an object is the whole thing, right? I could have a heat capacity of a calculator. I could have a heat capacity of a styrofoam cup. I could have a heat capacity of lots of different things. But when we want to talk about a material, and we want to talk about the material as an abstract concept, not as an object, we want to say plastic, styrofoam, water, diamond. How much thermal energy does it take to raise the temperature of 1 gram of that substance? Now we're talking about specific heat. And now we're not talking about a particular object, we're talking about the material in an abstract sense. How much energy do you have to put into that material to raise, hypothetically, 1 gram of it 1 degree Celsius? And that is the specific heat. It's the same idea, only we use a lowercase c with a subscripted sp for the specific heat capacity of a substance. The rest of the equation is the same. It's Q divided by delta T with the addition of the mass of the object also playing a role, because we're talking about how many grams now are in the object. So if it's only 1 gram, then 1 times delta T, the M doesn't matter. And the term C lowercase or subscripted SP means the heat capacity of 1 gram of that thing. But if we have an object that weighs, 5.4 grams, then you've got to account for that in your math, and that's where that M term comes in the denominator there. Okay, so specific heat and heat capacity. So here's some pictures to help you understand a little bit. Up in this top area up here, I've got a pot of hot water. And if you were to hypothetically put a metal spoon and a wooden spoon in the same pot of boiling hot water, and then were to grab them, I wouldn't recommend that because the metal spoon will get very, very hot Why does the metal spoon get hotter than the wood spoon? Because metal has a very low heat capacity or a very low specific heat. And so as we're adding the thermal energy from the boiling water, the metal spoon's temperature will change rapidly. And if you've ever left a metal stirring spoon in a pot of boiling water and then gone to grab it, you'll know what we're talking about. But a wooden spoon is preferable in many situations because the wood has a very high specific heat and will absorb a lot of thermal energy before its temperature changes. This also gets to heat conduction, which we'll get to later. But the wooden spoon is going to be a lot gentler on your hand because it can absorb a lot of thermal energy before its temperature changes. One of the highest thermal energies, one of the highest heat capacities of any material is actually liquid water. Liquid water absorbs scads and oodles of thermal energy before its temperature changes, which is why a pot of boiling water takes a lot of time on the stove to get boiling. You're adding lots of heat with all that fire under the pot, but the water doesn't boil for a long time. That's because it's absorbing tons of thermal energy before its temperature changes. That makes it really good for regulating climate, and God designed it that way. So if water didn't have such a high heat capacity, the temperatures on the globe would fluctuate wildly between day and night. Temperatures on the moon are hugely different day and night. Temperatures on many of the planets vary wildly between day and night. It's actually the presence of all the water on our planet that helps our temperatures not fluctuate very much. So, here in Hawaii where we live, day to night temperature variations might be 15 degrees. In Flagstaff, where I lived before I moved here, day and night temperature changes were a lot more because we were higher latitude, higher altitude. There was less moisture in the air to help regulate the temperature. But when water is around, the temperatures don't change very much because it absorbs tons of thermal energy from the sun without allowing the temperature change in the environment to be very big. So praise the Lord for water's high heat capacity, and this little fish is rejoicing as well in its creator because its environment does not change very much in temperature because the water has a monstrously high specific heat. Okay, let me show you some pictures to help you understand that. So the specific heat of metals tends to be fairly small. And so this is the heat capacity of an object, and its unit is joules per kilogram per degree Kelvin. And so this is kind of a cumbersome unit, but the bigger the number is, the more thermal energy it can absorb before its temperature changes, right? So aluminum has a relatively small number. When you look at things that are much larger, like, well, helium and water, these are very big numbers in comparison to these metals. Diamond is even smaller. Diamond's temperature changes very rapidly. So the smaller the value for C, the less thermal energy it will absorb before its temperature changes. All right, so let's look at an example here, okay? So I have a glass pot, and in the picture there's water in it. Forget about the water for right now. We're just going to heat the glass pot, okay? The glass pot weighs 1 kilogram, and I am going to add 6,550 joules of thermal energy to the glass pot. And right now the glass pot is 20 degrees Celsius. You need to convert that to kelvins, so we need to be at 293.15 Kelvin. And remember, to convert degrees centigrade or degrees Celsius to Kelvin, you just add 273.15. Okay, so there we are, 293.15 Kelvin. Now, my equations, this is the one that's in your book. Heat capacity is change in thermal energy, I'm sorry, that should be specific heat, is change in thermal energy divided by mass times change in temperature. I'm going to rearrange this and solve for T. And so just doing some algebra, I get that the change in temperature is the change in thermal energy divided by the specific heat times the mass. Okay, so let's put that in here. Change in temperature equals 6,550 exactly joules divided by 840, that's the value for the specific heat of glass, times 1 kilogram. Times 1 kilogram doesn't change this. So 6,550 divided by 840 is 7.79761,904 Kelvin. That is the change in temperature, but that is not the new temperature of the pot. So to get the new temperature of the pot, I have to take my value for delta T, which is the change in temperature, and I have to add it to what it was before. It was 293.15 Kelvin. I'm going to add these numbers, and that gives me 300.94761, yada, yada, yada. I look back up here, I see 3 significant digits, 3 significant digits, 4 significant digits. I need to pick 3, so my answer is 301 Kelvin. Okay, that's the new temperature of the pot. If you need to see that example again, pause the video, play it again, do whatever you need to. Alrighty, now looking at the conservation of thermal energy. Like all forms of energy, it cannot be created or destroyed. It only changes forms. So when something gets colder or hotter, it's flowing thermal energy either from itself to something else or something else is flowing towards it. The thermal energy has to be accounted for. It isn't created. Something doesn't just poof get hot. So the thermal energy is either being created because some other form of energy is becoming thermal energy, like a chemical reaction, or because something hot has been put near the system that you're looking at and thermal energy is flowing to that system. Okay, so when we look at the math for this, we would say that the amount of energy in a system is inversely proportional to the amount of energy in its surroundings. So as it flows out of the system, it'll go into the surroundings, or as it flows out of the surroundings, it'll go into the system. They always balance, right? Or you could say that the sum total of the amount of energy in a system and the amount of energy in its surroundings is 0 joules. They cancel each other out. The change in one system is replaced by the change in another. Okay. Then there's this piece of apparatus we should talk about called a calorimeter. Calorimeter is something that measures the flow of thermal energy, and it does the best it can to completely contain thermal energy and not allow any to come in or out of a system, so that if thermal energy is being created by a chemical reaction, we can capture it all and measure it. Or if thermal energy is being absorbed by a chemical reaction, we can capture it all and measure it. Or if we want to put different things of different temperatures next to each other and watch the thermal energy flow, it keeps it only in those devices. So a calorimeter is something that contains thermal energy and helps you measure it. And we will use that in an example problem here. So for example, if I were to take some 40-degree water and pour it in the same vessel as some 60-degree water, the new water would be somewhere in relationship between those two. If they were the same volume, same mass of water, then it would be 50 degrees centigrade. If there were more cold than hot, it would be colder, or more hot than cold, it would be warmer. But the idea is that we're conserving thermal energy. You can add thermal energy with materials together, and thermal energy stays around. It's able to be calculated and handled, okay? And you can look at the relationship between temperature and its surroundings here. Here's a house, it's cold, it's winter, and the house has the heater on. And you can see that thermal energy is escaping through the roof. The roof is hot, and you could track the loss of thermal energy in the house, and you could track the increase in thermal energy of the air, and you'd be able to see that these two net zero. What the house loses, the air receives, right? So thermal energy is conserved. So let's look at a practice problem here for the way that you'll be calculating thermal energy flow. Okay, this is from your textbook. It's example 15.3, and it's called Finding the Little Foxes, which is a reference from Scripture. So the idea here is we want to see how much of the thermal energy the calorimeter absorbs in the course of this experiment. So 10 grams of water at room temperature is placed into a calorimeter. The equilibrium temperature for the calorimeter and the water is 20 degrees Celsius. So after it sits for a while, it's 20 degrees. Then 10 grams of the water is heated, then 10 grams of water is heated to 40 degrees Celsius and added to the water in the calorimeter. The new equilibrium temperature is 27 degrees Celsius. Find the heat capacity of the calorimeter. So we have here the system is the calorimeter, the cool water, and the hot water. You measure the water temperature and assume the calorimeter's temperature is the same at equilibrium. So the temperature of the calorimeter and the temperature of the water at equilibrium is all the same. The essential concept at work here is this. After the hot and cool water mix, you determine the heat gained and lost by the two quantities of water. Any difference of heat must be due to the heat transfer to or from the calorimeter based on the conservation of thermal energy. So again, conservation of thermal energy. You have the volume of heat in the hot water, volume of thermal energy in the hot water, the volume of thermal energy in the cold water, the volume of thermal energy in the calorimeter. And if you look at the changes in all of those, it should equal 0 joules, because all of these will gain or lose energy and pass it back and forth amongst the three of them, but it won't leave the calorimeter system. Okay, so calculate the heat transferred from the cool water. Here's the heat, the thermal energy of the cool water, and this is just a rearrangement of the same equation we've used a couple of times in examples already, where you have the specific heat of a substance and the mass of the substance and the change in temperature. Okay, so mass, specific heat, change in temperature of the cold water. If you then look at the change in temperature from the final to the initial, the cold water went from 20 degrees to 27 degrees. So 27 minus 20 is 7. And then you plug in the value for the specific heat of water and the mass of the water in grams, and you multiply across, and you get a gain in thermal energy of 292 joules. Then calculate the transfer of the hot water. So it started at 40, it ended at 27, so the change is 27 minus 40, which is going to be negative 13. There you go, I can do math. Negative 13 times, again, 10 grams and the specific heat of water. 10 times that times negative 13, and you get negative 543.4 joules. So we have now the change in energy of the hot water, change in energy of the cold water. We need to calculate the change in energy of the calorimeter, what happened to the calorimeter. And all of that should balance out to 0. So you can solve for the change of energy of the calorimeter, just bringing these two over to the other side, minus these two, right? And then you plug in the values that we got. And the change in the calorimeter is that the calorimeter gained 251 joules of energy. So the calorimeter heat capacity is calculated from 15.1. We are told that the calorimeter, heat capacity calorimeter, we calculate that, there you go. As a heat capacity, we don't need the mass of the calorimeter because we're not doing specific heat capacity of the calorimeter. Is the change in energy and the change in temperature. The calorimeter also went from 20 to 27. So it gained 251 joules divided by the change in temperature, which is 7 degrees. 251 divided by 7 is 36, well, 35.8, and then significant digits brings it to 36 joules per degree centigrade. So that is the heat capacity of the calorimeter. Okay, replay that example again if you need to. All right, latent heat of fusion and latent heat of vaporization. These are concepts you had already in chemistry, and you had them also in physical science, but we just defined the term. We didn't give you any math. This is math because it's physics. Yay, aren't we in love with math? So, latent heat of fusion, or L sub F, and latent heat of vaporization, L sub V, describe the amount of thermal energy change required to melt or freeze, boil or condense a material. So melting and freezing has to do with fusion, boiling and condensing has to do with vaporization, and it's the same value, as just a sign change difference, right? And so we express this in joules per gram, how many joules it takes to melt or boil a gram of a substance. During phase changes, the temperature doesn't change. We already know that. Water, while it's boiling, is always 100 degrees Celsius, right? Assuming you're at sea level, which in Hawaii we almost always are. All the thermal energy transfer goes into the phase change. So as heat's being added to the system, the heat is not making the water hotter. The heat is making the water turn into vapor. So latent heat is called latent heat because it's heat that doesn't change the temperature. It goes into the background and it does things to the material. Okay, so we calculate latent heat of fusion by looking at the amount of thermal energy it took to melt a substance divided by its mass. Or the liquid heat of vaporization is the amount of heat it took to boil a substance divided by its mass. Okay, so that's a pretty simple, straightforward equation. And just again, so that you can see the fact that temperatures don't change while a substance is freezing or boiling. Here we have a solid that's extremely cold. And as we heat it up, the temperature rises while we're putting more energy in. So energy goes in, temperature rises until it gets to the melting point. And then while the solid is melting, we're still adding more energy, but the temperature is flat. It's not getting any hotter while it's melting, okay? Then once it's a liquid, the temperature rises again until we get to the boiling point. Then we're adding more energy still. The energy input is still positive, but the temperature is flat. And again, the temperature does not change while it's boiling. Then while after it has boiled, after it is a vapor, a gas, then the temperature can rise again. Okay, so this is just a graph. You've seen this kind of graph now 3 times, lots of times. Hope that this is a remember thing for you and not a learn thing. So here's how this works with regard to doing some example problems. We're going to calculate the heat of fusion for water. So we have 10 grams of ice, and so that's ice that is obviously a solid. And we're going to place it in the calorimeter with a heat capacity of 36 joules per degree Celsius. So we already know what the Q for the calorimeter will be. And the equilibrium temperature is 0 degrees. Everything is at 0 degrees, right? Because the ice is frozen. Then 20 grams of water at 50 degrees is added. So we've added 20 grams, twice the volume of relatively warm water into the calorimeter. The new equilibrium temperature after the ice has melted and the water has gotten colder, but the ice has gotten warmer and the calorimeter has changed its temperature, is 5.2 degrees Celsius. The ice has melted. Calculate the heat of fusion of the ice. So heat of fusion, latent heat of fusion, is the quantity of heat it takes, thermal energy it takes to melt a substance divided by its mass. You could rearrange to put Q melt outside, and solving for the quantity of heat, then that is the mass times the latent heat of fusion. Okay? Note which quantities are changing and which are constant. The ice melts, but its temperature doesn't change. The cold melt water from the ice, so then CW, cold water, warms from 0 to 5.2. And the warm water, CWW, warm water, cools from 50 to 5.2. The calorimeter experiences the same temperature change as the cold water. It was 0, now it's 5.2. Therefore, heat flows from the warm water into the ice melt and into the resulting cold water and into the calorimeter. Find the conservation of energy in an adiabatic container. So adiabatic, that's a nice vocabulary word. That means it's a barrier to temperature flow, to thermal energy flow. It's an insulator. That's a much nicer word for it. So the quantity of heat that changed in the calorimeter and the quantity of heat change in the cold water and the quantity of heat change in the warm water and the quantity of heat change needed to melt the ice is a total of 0. All of the changes balance each other out. So we're going to rearrange that so that the quantity of heat needed to melt something is by itself in the equation. And then that is just the negative of these other 3 added together. Because if you look up, here they are all on one side of the same equal sign, and then that's 0. So we're going to bring all of this over. So Q melt equals negative all of these things, right? Okay. Substitute equation 1 for Q melt and solve. So Q melt was also the mass of ice times the latent heat of fusion. So mass of the ice times the latent heat of fusion equals now this. We've just substituted 2 equations that had the same term. Now I can divide by the mass of the ice, and I get this. Latent heat of fusion is the negative of the sum of the thermal energy change in the calorimeter, thermal energy change in the cold water, thermal energy change in the warm water, divided by the mass of the ice. Calculate each of the heat expressions, so I need to know what each of these things are. So for the calorimeter, it's C, the quantity of heat, the heat capacity, there you go, times the temperature change. So heat capacity was given to me, times the temperature change of 5.2 degrees, gives me this. The mass of the water, specific heat of the water, temperature change. Mass of the water, specific heat of the water, temperature change, gives me this. Mass of the water, specific heat of the water, temperature change, warm water. This was cold. Here it is again, and the warm water got colder, so that's that. So now I put these three values in right here. I add them up, I change the sign, I divide by 10, and I wind up with 334 joules per gram. That is what I'm saying is the quantity of energy that it took to melt the ice, right? 334 joules of energy per gram of ice. And that is, then in significant digits would be 330 joules per gram. And if you look at a table, that's very close to the accepted value. The accepted value, I think, is 331 or something like that. So this would be very, very good experimental results in the lab. Okay, and lastly, there are three methods of thermal energy transfer, three ways that heat can flow. And this is totally review. You had this in 9th grade and in 11th grade. And here you are, a strong, robust, God-fearing senior. And you already know this, but I'll tell it to you again because I like reviewing. The three methods of transferring heat energy are conduction. That's when two things come into contact with each other. So hot something, cold something, touch, and the heat energy flows from the hot thing into the cold thing. Okay. Convection is when you have a hot thing and a cold thing usually above it, and the air or the fluid between the two carries thermal energy between two objects, and you get a stirring of the medium between them. You get things called convection currents. As hot air or hot liquid rises and cool liquid or cool air settles, it starts to stir, and that's a convection current. Okay? And then radiation is when thermal energy flows across a vacuum to another object. And this is the best example of that is the sun, where the sun shines its thermal energy on us through the vacuum of space. Now, sometimes we also say that holding a hot object near another object so that you can feel the thermal energy on it is also radiation. Radiation can happen through a medium as well, but the classic example of radiation would be through a vacuum. Okay, so those are the three methods of heat conduction, and that is the essential knowledge for you for Chapter 15. If you have any questions, post them in the comments below. God bless you. I'll see you tomorrow.